All right, hello everyone. My name is Steven. You guys might have seen me at the opening ceremony. I was the founder of Curious, and tonight I just happened to give a workshop on cryptography. Super excited to be teaching or giving a workshop on this topic. So a little bit about myself. Currently, I'm a student at Waterloo studying software engineering. I will say this, that I am not an expert per se in the cybersecurity space. I'm still a student, but it is a topic that's pretty interesting to me tonight, which is why I decided to give this workshop. So I'm going to do the best I can to teach you guys as much as possible. Now, before we head into the workshop, I want to ask you guys, what is your experience with programming so far? Because I want to get a feel of sort of the audience I'm working with, as well as I want to ask you guys about your experience with cryptography, if you've even heard of it, but we're going to do that a bit later. First of all, can you guys let me know in the chat, what is your experience with programming, what languages you've written, and how long have you been programming for? That'll be really helpful, because there's going to be part of the workshop where we're programming. So I want to know if I have to explain to you guys what variables are, the return types, like all of that, or we can kind of blaze through that. Awesome. So Rick has zero experience with cryptography, but 5 years plus of programming CS courses in high school. Awesome. What about you guys? Emanuela, Ethan, Ayesha, I see all of you guys. So if you guys could let me know, that would be really helpful. If not, because this is sort of the first week of the Learnathon, I was thinking to make it more beginner friendly. And so the programming we're going to do, we're going to look at some like simpler ciphers. But I think there's some stuff to learn still, but I'm going to assume that most people have a more beginner experience. Okay, if you had novice to programming, zero experience, 2 years of programming. Okay, cool. So you guys have some 3 years for. Okay, so you guys have quite a good. What languages are you guys familiar with? Is it Java? Is it Python? Okay, Java. C++. Okay, I was planning to do tonight's workshop in C++. So I think because we're going to be working with characters and strings, I think it'll be interesting, because I think in C++ it's a bit easier to work with the characters. But anyways, okay, good to know. So let's start the night off with the Mentimeter. Yeah, I think you guys still see this. So I want you guys to go to menti.com and use the code 43292469. And I want you guys to sort of fill this. And I can put it in the chat. And this is, I think, the shorthand link. So go there, and I want you guys, without Googling or anything, just think of cryptography and try to describe it in 3 words, and let's see what you guys come up with. Security, ciphers, encryption. Okay. Yeah, just throw it out there. I want to see what you guys think cryptography is about. Also, welcome, Edward. Good to see you. Computers, hacking, awesome. I'd like some more responses. I know there's more of you in the Zoom call, so I'm gonna give it 1-2 more minutes. Really, like, just don't worry about giving the wrong answer or anything. Just I just like to have an answer, see some words, and that allows me to work with a little bit of material and discuss maybe even some misconceptions and things not to confuse cryptography with sort of other concepts. Awesome. Okay, we'll give it 1 more minute. Okay, awesome. So I see some really interesting words here: encryption, quantum computing, graphing, crypto, ciphers, cryptographic key. Awesome. Deciphering and graphing. Yeah, I think it's good. So I see the word crypto here. So I think especially for people who've never sort of heard cryptography or not familiar with the space, you might easily confuse the words like cybersecurity, cryptography, and cryptocurrency. Um, I think this workshop, it's a series of, I think, 3 or 4 cyber workshops. And this first one is on cryptography. I think there's going to be one on cybersecurity, and I think one on blockchain and cryptocurrency, maybe. Correct me if I'm mistaken. But essentially, cryptography, you can think of it as a specific application of cryptocurrency. So cryptocurrency uses cryptography to make the blockchain, because it's built on blockchain, and that's how it makes it work. But they're not the same thing. So when we look at cryptography, so I'm going to get out of Mentimeter. Go back here. When we talk about cryptography, what we're talking about is the practice and study of techniques for secure communication in the presence of adversarial behavior. So actually, cryptography hasn't been a thing just in the last century. It's been on for thousands of years. It goes back to the Greeks and the Romans, because for thousands of years, humans have been trying to keep secrets, right? And humans have been trying to find ways to send these secrets securely. Say I was living in France and I wanted to send a secret message to my friend in England. How would I needed to come up with a method, right? To if I didn't want others to read this particular message, if I only wanted my friend in England to understand that message, I needed to find a way to encrypt it. So encryption meaning converting this understandable message into something that people can't understand, except for the person I'm trying to send it to, because they're going to be able to decrypt it into the original message. So traditionally, when we look at cryptography, we can, I wrote here that it serves 2 main purposes. Number 1 is keeping secrets. So with the example I just gave, if I have a secret, I want to send it to only for myself or a specific group of people. Cryptography, offers sort of these methods to encrypt it. But over the past sort of century or two, with the rise of the computing era, one of the other really interesting applications of cryptography is proving identity and knowledge. And so we're going to go into that a bit later tonight, talking about this. But at a high level overview, it's this idea that if I'm sending a message to, say, my friend Edward in the chat, right? If I'm sending him a message, how will he know that it's me who's sending this message? So how can we prove that? And then this is a very interesting concept, I think. And so what we're going to be talking about is the concept of symmetric and asymmetric encryption. So one of the words mentioned in Mentimeter was this cryptographic key. So that's going to be one of the ideas we're going to go back to later. There's going to be public keys and private keys. It's very interesting. So we're going to get to that later. But for now, I think in the first part of tonight, we're going to be talking about first classical ciphers. So this is sort of the era before the computing era, when people were mostly working with pen and paper. And then we're going to be looking at the modern cryptography. As I said, I'm trying to make this a bit more beginner friendly. And so the modern cryptography stuff, there's a lot of really more like complicated concepts. There's a lot of math involved. There's prime factorization. So you need some background in math to understand it. So I'm going to do an introduction later tonight about that. But in the first part, we're going to be looking at classical ciphers. All right. So as I said before, before the modern era, the classical sort of cryptography, we were really focused on just the keeping secrets part. So that was ensuring that the message that was being sent was going to stay confidential. And this is where we encrypt stuff. We convert something that we understand into something we don't understand. So within that family of classical ciphers that's concerned with preserving these secrets, we have really sort of two ways about going it. And so here I say classical ciphers are mainly concerned with encryption using linguistic and lexicographic patterns. So in the past, really, it was the messages that you were sending over, and you were trying to encrypt that message, right? So these were like, let's say, sentences in English or sentences in a particular language. We're going to be looking just at English for today. But if you have like a Roman, Greek language, it's very similar. So there's really two main families within these classical ciphers. Number one is substitution ciphering and transposition cipher. And before I even explain what these ciphers are, I just want you guys to put into the shoes of say the emperors at those times. So in the past, most of the time that people were using ciphers were for wars, right? Because in war times, you're trying to tell your commanders things to do, and you don't want your enemy to know, right? Because if they intercept the message and they can understand it, then your whole plan is compromised. So I want you guys to think for a moment and tell me, like, if you were an emperor, you had some sort of message that you wanted to send to people, your commanders or your captains, how would you encrypt your messages? Just try to think about that. And we're going to go from simple methods to a bit more advanced methods, and see if we can even come up with a more advanced version of encryption. And as a hint, there's these words like substitution ciphering, transposition ciphering, monoalphabetic, polyalphabetic, polygraphic cipher. If anyone wants to unmute or just type it in the chat, if you were to make a cipher, how would you make it? Something that, a certain way of encrypting your message, and then, the person who receives it, they should know how to decrypt that message. Anyone has a proposition? What is the simplest way to encode your message, say, into something that people don't understand? Switch around the letters. Yeah. Shift letters and or replace those letters with runes. Exactly. So at a high level, switching around the letters, if it could be either substitution or transposition ciphering. So let's start with the simplest one, which is sort of shifting the letters in this conventional way. So this was a method that Julius Caesar back in 70 BC came up with, and it was one of the simplest ciphers, but it worked back in the times. And what he would do is, say you have a message like A, B, C, D, E, F. What you would do is you take each of these letters, and instead of using this letter, the encoded version would just take that letter and shift it by a certain amount. So there's a mapping of, say in this case, the letter A becomes the letter X, the letter B becomes letter Y, letter C becomes letter Z, letter D becomes letter A. So there's a shift of 3 characters for each character. So D, instead of being D, it's got shifted 1, 2, and 3, so it becomes the A. The E becomes shifts by 1, 2, 3 to the left, so it becomes B, and etc. And for A, because there's no letter before A, it just gets back to Z. And so this is the simplest, sort of one of the really simple ways of encoding. All right, so I'm just reading Shubham's message. So this is really interesting. Let's get back to that later. And if you want to unmute and explain your method, maybe we can even code your way of encoding this algorithm. But to start off the night, we're going to come up with this algorithm to encode and to decode our original text. And I'm going to be using the terms plain text and ciphertext. So plain text refers to the original message, the one that's not encrypted, whereas ciphertext is the message that's encrypted after applying the algorithm, the Caesar cipher that we're talking about. So what we're going to do is I want you guys to open up, if you don't have a C++ installed, what I'm going to do is I'm going to go on an online C++ compiler over here. So the link is, if you guys want an online compiler, is this. So we're going to be writing some C++. If you guys don't know C++, that's totally fine. I'm going to be explaining some of the grammar to you guys. But the reason I chose C++, I don't know if Java has this functionality as well. But basically, in C++, the way characters work. So I'm gonna pull up an ASCII table over here. So in C++, let's see, let me find a good table for you guys. So if you look here, this is an ASCII table, open copy image address, and then we're going to go to the image address. So this is an ASCII table. And essentially what this is right, you guys think of these characters as characters, but actually the way the computer understands them is as numbers. And in C++, what we can do is do arithmetic on these characters. So for example, if you take the character A in decimal value is 97, right? So what I can do, for example, so in C++, I'm gonna write something and I'm gonna explain the syntax. So give me a second. I'm just gonna show you guys what this is. Run this. So you see, what I did here was I declared a variable called A. And this character is of type char. So if you guys work with Python, you don't specify the type in front of the variable. But in this case, this variable is a char, which is a character. It's different from a string because a string is basically a group, like a bunch of characters together. So each of the element of the string is a character. And so I define the character A as the value A. Maybe this is a bit confusing. So if I rename it to character, I can do that. So I set it to A. And then here, this is actually C code, but it works in C++ as well. But what I'm doing is I want to print a variable as D, as a digit, and then the actual variable I want to use. Now in C, they have, as Ethan mentioned, count. But if I were to use count in this case, it would not work because this would print, oops, this is character. This would print A because when I do %d, what I'm actually doing is I'm forcing the variable to be casted as a digit, as an integer. But by default, they work as a character and they're going to represent it in this character form. But if I explicitly force it to be a digit, which is what I'm doing here, then it's going to print out 97. Now, the reason this is important, why I'm talking about this, is because this makes our life much easier when we're working with these characters. Because instead of, say, writing a map, right? So if, say, in Python, for example, what we would do is like you can do a map, or maybe there might be a simpler way they have it in Python. But you know, like when I was first starting out, like whenever I was working with strings, like what I would do is like, oh, I built this map. So A is associated with 0, B is associated with 1, C is associated with 2, etc. Like I would hard code this, and then I would do the shift, whatever manipulation I wanted. But in C++, it's really simple. So what you can do, for example, if you want to know the distance between two characters, so like say, how far is the letter C from the letter A? We know it's 2, right? Well, if you look at here, oh God, I'm gonna move this. Oh no, this thing above is hiding. Okay, there we go. If you look here, the character A is 97. A character B is directly 1 bigger than A, 98. C is 99. So you can just do C minus A, right? The character C minus A, and that's going to give you 2 as a result. So let's try that. Just to prove to you guys that it works. If I count, if I C out, if I print it out, A, C minus A, I run this, it gives me 2, as you guys can see. Is this clear so far? Is there any questions? Okay, what is a Python dictionary? So this is a data structure. This is a more advanced concept for you guys out there. I'm not sure if I want to talk about this for beginners, but I think I'll mention this. Essentially, a dictionary is like it's also known as a map, but essentially it's like a mapping of a certain thing to another thing. So for example, we give a mapping from a string to an integer. So for example, if you want to track, say you have a string, hello world, and you want to count the number of occurrences for each of these characters. What you can do is have a map, which is like a table, and say what it does is, for example, if I declare a map, so I said let's do a mapping of character to integer. What you can do is you go over the string and you look at each occurrences, and you can store this in a map. So every time you encounter a particular character, you're going to store for that character the number of times you see it. So there's a lot of really useful, really good use cases for a map or a dictionary. But I think for this workshop, it's a little bit outside the scope, but I can give you guys, I can briefly talk about that. Ethan, is there a question you have about pointers? Okay, sounds good. So is this clear so far? So far I'm talking about characters and strings. Characters are, a string is composed of characters. It's one specific element of the string. And notice how I use the single quotes instead of the double quotes for a string. And this is a really important distinction, because if you do like this, then this is would be a string and not a character. That is really important. And that's a mistake I make, because in Python, they don't make that distinction. But in C++, you need to be careful and make that distinction. So far, everything clear? Again, the cout, this is sort of printing in C++. In Python, it'd be like print something, hello world, right? In C, what you can do is do cout hello world, like this. And the end line here basically just prints a new line. Python automatically takes care of it for you. So if you do print hello world and print hello world in Python, it would just print them in 2 separate lines, because every time you call the print function, it automatically creates a new line. But in C++, you need to do it manually. Okay, so let's get back to our main objective. We're trying to code a Caesar cipher. So I want one of you guys to tell me what message do you want to send over to someone else. And we're going to make that our string. And by the way, this is not good syntax. String, let's name the variable plain text. Can someone give me a message you want to send over? Maybe like curious workshop. Oh yeah, okay. So Pranav told me you can definitely do it in Python as well by turning it into a hexadecimal value, which is another format. So in C, oh my God. Okay, there we go. I moved this to the bottom. Okay, so in Python, so you guys see how the character, it has a decimal value and a hexadecimal value. So in Python, I guess you can use the hex function and turn the character into a hex value. It's different from the decimal value, but the difference between, say, character B and A is still 1. So the same logic works. But we're going to stick to C++ because I think it's a bit more challenging and fun. So we have the original message, a curious workshop. We want to encode this. So let's write a function to encode that. So with the Caesar cipher, we're going to, the syntax for a function in C++ is, first of all, you specify the return type of this function. So we want to return a string. Therefore, the return type is string. And then we're going to name this function Caesar cipher. Or let's call it Caesar Encrypt, because it's an encryption with the Caesar function. And what is it gonna take as an argument? Well, we'll be taking a string, and what the string will call the variable plain text. Now with the Caesar cipher, we also need to specify the shift amount, right? Whether we want to shift that by 0, by 1, by 2, by 3, we can specify it as a variable. So that's sort of, we give you the customization, and we're going to name that the key, okay? Because without this key, you wouldn't be able to decrypt the message, right? Because you wouldn't know how much to shift the encrypted message, the ciphertext, which is why this is a key, because this is the key to decrypting the original message. So this key is just a number. It's going to represent how much we want to shift the number by. Okay, everything clear so far? Or is there any question? How would you program an AI to break the cipher? Okay, this is really, so we're going to get into this a bit later. We're going to talk about the techniques we would use to break these ciphers. Just as a quick preview, it's something called, for classical ciphers at least, it's something called frequency analysis. So keep that in mind. I'm not going to tell you what that is, but just keep in mind the word frequency analysis. That's a technique that we're going to be using to crack these ciphers. Yeah. All right. So with Caesar ciphering, with Caesar encrypting, right? What do? Well, we take the original plain text and we're going to shift every character, every element in the string. So the way we can do that, okay, so how many letters are there in the alphabet, guys? I forgot. Someone let me know. 26. Thank you. So we have 26 letters. Okay, so first of all, we got to make sure that our key, and this is to make our lives a bit simpler, right? Say I'm telling you to shift my thing by 56. Shifting a letter by 56 is like the same thing as shifting it by 26, right? Because there's only 26 you can shift. If you shift it by 26, that's sort of there's a circle and you get back to 0. So what we can do is modular arithmetic. So to make our life simpler, we're gonna first make it down, break it down into some number under 26. And so 26, sorry. And so this is the modulo function. So what that does, this is where there is a little bit of math. But essentially, if you have a number like 27, you're going to keep subtracting 26 to this number until it is within the range of 0 to 25. So if it's 26 modulo 26, the answer would be 0. If it's 25 modulo 26, it would stay 25. It just allows us to bring this number back to a number under between 0 and 26. So 0 inclusive and 26 exclusive. And this is not really necessary, but I think it just makes my brain work a little. And if it's negative, yeah, it is the remainders. Yeah, that's the term. The remainder of it's the remainder after say 27 divided by 26, the remainder would be 1. And this, yeah, just gives you the remainder. So we have this key. So this is how much we want to shift it by. So say, for example, our key is 2. Now we want to shift each of these characters by this number, right? So what we can do in C++, you can iterate over the string using a for loop, just like in Python. So we're going to do for each element in the string, and okay, I'm going to write it out for character C in plain text. So what this is going to do, for example, if the string is a Curious Workshop, it's going to go over this character, then this character, then this character, then this character, then this character, and it's going to loop that until you reach the end of the string. So for each of these characters, we want to shift it, right? And also, after we shift it, we want to store this in a final string. So this final string, it's the ciphertext. So we're going to initialize it to an empty string, and then every time we're sort of shifting the original plain text, we're going to add it to the ciphertext. And that can be done just by doing a plus equals. And so this is the same thing as ciphertext equals ciphertext plus something. Right, so I'll just keep it in this form for now. so you guys can understand better, I guess. So what do we do with each character? We want to shift it by the key amount, right? So all we can do is really do arithmetic. So we're going to add the character by the key value, right? So C plus key. For example, A, if you want to shift it by 2, if we refer back to our ASCII table, if we shift the A by 2, so 97 plus 2 will be 99. And so we would just get the character C, right? And then at the end, we can just return the ciphertext. And that is the function, right? Are we done here? Are we done here, or is there something else we need to do? So let's try and run this. So let's call our Rsa Encrypt, and let's use our argument plain text, and then say we want to shift it by 2, and we're going to print so this would be our ciphertext, and we will print it out. Ciphertext, and if we run this, then character. Let's see if the version ciphertext. Okay, for some reason, ciphertext equals C plus key. So as you see, we have A is shifted by 2, so it's C. Now the thing with the space, and this is why it's with space, it's a little bit weird. So because if we look here, the space in the table, the space also has a decimal value, but it is not in one of these values. So if we have to look at space, I think I googled space ASCII value, and the number is 32. So we look here, 32, which is a space, and plus 2 will be this. So our space doesn't really work. So what we can do for now as a cheat is just removing the space. And I think if we do this, then all of them are encrypted, and we have this shift by 2. Now the problem is we need to use modular arithmetic. So Rick, you are right. Don't say never mind, because if you look here, if we shift Z by 2, in theory we should have B, because Z shifted by 1 is A, shifted by 2 is B. In this case, we have this vertical pipe, which makes sense because if you look at Z and you add 2, it's this vertical pipe. However, we actually want it to be B. And so we need to use modular arithmetic, but it's not as simple as doing modulo 26, right? Because this number is not 0 to 26. It's actually 61 to 120, 97 to 122. So what we can do is we want to add the original character. We want to add it. We actually want to start from A, and then we want to take the. So how do we do this? So do painting. So say we have the letter. What letter do we want to use? Let's use D. Okay. D is 64. D is 64. But, and we want to shift it to let's use Z, right? Because that's the most challenging example. So we have Z, and this has a value of 122. And if we shift it by 2, we want it to be B, but B has a value of 62. So what we can do is first convert this letter from a 61. We want to convert this letter from a 61 to 122 scale into a 0 to 26 scale, right? And so what we can do is, first, to do that, we can just subtract the character A, which has the value of 61. All right, so we're going to take the original string and we're going to subtract it by A. Original character, sorry, because characters and strings are different, as I mentioned. So that will scale it down into a value from 0 to 26. And then we're going to shift it by the key amount. So say we want to shift it by 2. Say we want to shift it by 2. So this will be A. This would be Z. And let me erase the, oh God, new. Don't save. Okay. Let me redraw this. So we have A. We have, oh, why is, don't save. Let me try this. Paint. We have A, which is 61 in decimal value. And we have Z, which is 122 in decimal value. We want to convert it to a 0 to 26 scale. So what we can do is just subtract A, which is equal to 61. And then we're going to shift by whatever key value you specify by key. So say it is 2, then you're going to shift this first A plus 2. All right, and this last one, you wanna add 2 to it. So it'll be 26 plus 2. Oh wait, there's this. Okay, Z, since this is 0 indexed, Z would be 25 because there are 26 letters in the alphabet. So we go from 0. If A is 0, then Z would be 25. So sorry about this confusion. So this will be 25. How many letters in the, oh, sorry for these embarrassing. This is an extension I used. I don't know what I wrote, but it's okay. There's 26 letters. So let's do it. It should be modulo, let's see, 20, it should be modulo 26. Yeah, it's modulo 26. So we shift it by the key. And so in this case, it'd be 25 plus 2 modulo 26, which would give us 27 modulo 26, which is 1, which corresponds to B. Because A is 0, B would be 1. And then this would correspond to C, right? And so the logic here is you subtract the original character by A, you shift it by the key, and all of this, you're going to take it modulo 26. And that should give you your answer. So for example, for A Curious Workshops, and you run this, the Z should be like calc, cipher, plain text. Why is not printing? Plus subtract the original character from the C, and you're going to take modulo 26. Oh, yes. But now this is on a 0 to 26 scale, right? Because what we did here is convert it from a 0 to 26 scale. Now we want to convert it back to the hex, the decimal value. So we're going to all of this, and we're going to add it to A. And that would give us the characters in the right values. So now if you run this, then this works. All right, so this is how you would do it in programming the Caesar shift, the Caesar encrypt. Now, of course, if we send it to our friend, we need them to be able to decrypt it, right? So let's quickly use the same function, but instead of Caesar encrypt, we're going to do Caesar decrypt. And it's the same idea, but instead of moving it to the right, we want to move it to the left. So here we're going to subtract the key. And we can, let's add 26 to it, because if it's a negative number, unfortunately in C++, they don't take care of like making the negative number positive. So we're just going to add 26 to it to make sure it's positive. And again, we're going to take the modulo for it. And now if we do, so now let's say the encrypted message is the following. I'm just printing it out to make it more clear. And then encrypted message, put the Caesar decrypt, and then we're going to take the ciphertext, we're going to shift it by 2. And now if we look at the decrypted message, we should see A Curious Workshops, decrypted message. And let's make this more readable. So you see, the encrypted message would be this. So this will be the message you sent. Let's say I send it to my friend in England. I would use this string, but afterwards, my friend, to decrypt it, he would use this key 2, and he would shift all of these back by 2, and then now you get the original message. And so for people who intercept this message, they might be able to see the message, but they have no idea what we're saying, this gibberish here. And so Julius Caesar came up with this method in the 70th BC. So that was a long time ago. And yeah, it just shows that it was pretty creative that he came up with this that long ago. Does anyone see any problem with this? Like say I intercept this message, like would I be able to, I don't know, I can't tell, but would I be able to decrypt it somehow? Yeah, you can brute force and solve it easily, right? So that's the problem with the Caesar shift. Because there's only so many shifts you can try, right? You can shift it by 1, shift it by 2, shift it by 3, shift it by 4, all the way until shifted by max is 25. Because if shifted by 26, then it's the same thing as shifting it by 0. So there's only really 26 possibilities of shifting. So you can just try and brute force, and until you see one sentence that makes sense, and that would be you would find the key for that, and you can find the original message. So that's the problem with the monoalphabetic cipher. So then now, and monoalphabetic here merely means that you are using a single alphabet as a mapping for the original message, right? So you're taking each of these string and you're using your own alphabet to change it. Now, it's not in here, but a more advanced version, instead of shifting all of them by a constant. So, oops, this is my code. Instead of shifting all of these by a certain constant, what you can do is, write your own mapping. So say, let me close this, and let's use Paint. And I could say, okay, I want the letter A to be the letter C. I want the letter B to be the letter Z. I want the letter letter C to be, say, letter E, letter D to be letter F, etc. So you write your own sort of map, making sure that all of these letters are only used once for your own key. This would be like the key. So Z is like H. Like make sure all of these are used once, so like there's no two letters that mean the same that have the same encrypted value. And this will make it a little harder, right? Because then you can brute force it, but for each of them, you have to try 26 different ways of doing it. Then for letter B, you have to try 25 ways of doing it, then 24. So it'd be 26 factorial. So that would make it a little hard, much harder, and that would still be mono alphabetic encryption because you're using a single alphabet. But that can still be cracked. And I'm gonna explain a bit how you can crack that. Again, it's frequency analysis, right? But Mr. Wigner here in 1553 came up with an interesting idea that's built on top of the Caesar shift idea. And this actually resisted all attempts to break until 1863, which is 3 centuries later. So this lasted 3 centuries, okay? And so, what is this? The French, I think, they deemed it like the impossible cipher to break for 3 centuries. So this is quite resistant. And the reason this is so resistant is because it is a polyalphabetic cipher. So there's an additional layer of complexity to this. And if you guys look at this table, this is the table we're going to reference to code our Wigner cipher, right? So we're going to go back into our code, and we're going to implement this cipher now. This cipher uses the Caesar cipher. But what's really interesting here is that instead of shifting each character by a constant value, what you're going to do is shift them by a specific value defined to you by the key. So let me explain. Let's go into Paint. Oh, can you guys even see my paint? Wow, why did nobody tell me that? Oh no. No, I was explaining my paint, guys. Oh no. Okay, I'm sorry about that, guys. Yeah, I was explaining my paint. Yeah. So this was what I was talking about. If you just use, damn, I'm so sorry, guys. Why did nobody tell me? Now you can see it, of course. Anyways, close this, Paint. Oh, thank you. My explanation was so good. We can imagine. Oh, I was making a lot of effort to draw it. Okay, but now that we have Paint open, let me try and explain this because I think visuals really help the explanation. So in the Wigner case, right? So in Caesar shift, what we did is we took, say, the letter A and we shifted by a particular amount, like 2, and that would by 2, and that would become C, right? And each of these, so say I have curious. What I do if I say shifted by 2, K, what comes out to K? A, B, C, D, E, F, G, H, I, J, K, L, M. So this will be M. You do +2, etc., right? But what you can do is you take a key. So say my key is A, B, C, D, okay? So this key, what you're gonna do is say the word you wanna send over is curious. What you're gonna do is you're gonna take this key. So this there's 1, 2, 3, 4, 5, 6. There's 6 letters. So you're gonna repeat this key until get to the end and repeat it as many times. So here I have A, B, C, D, and then A, B, but I would keep going if there were more words. So if there was like I, U, S, then you do C, U, C, D, A. So you just keep repeating the string, keep repeating this key as many times as you need to until the very end, so that you have this sort of mapping. And then what you're going to do is you're going to take each of these characters, and each of these characters in the key represent a particular shift. So in the case of the letter A, that would represent a shift of 0. If you look at my presentation, the letter A, so if you look at the row here, each of these represent how much you want to shift it by. So the letter A will be representing by a shift of 0. So A in your original plain text, if it sees the key A, then you don't shift it by anything. But for the letter B, the letter A would be shifted by 1. So the letter A would become letter B, and the letter B would become letter C, and etc. The letter Z would become letter A. If you reach the letter F, then letter A would be shifted by the F amount. And so that way it makes it a bit more complicated, right? Because the shift amount is really different every time, and you can't really brute force it because you don't have the original key. And also this key length is variable, right? So again, I'm going to try to explain it in here. So say my original string was hello curious, right? And my key is A, B, C, D. What I'll do is I'll repeat A, B, C, D as many times as I need until they match in length, right? So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And my key is A, B, C, D. I would repeat A, B, C, D until the very end. And then I would use this table that I have from the Virginal Cipher, sorry. And then I would shift each of these. So I guess in that sense, it is some sort of equation. And so what you would do is we're going to use the Caesar shift again, the Caesar encrypt, but we're going to do a variation of it, right? Because each of the characters are shifted by a different amount. So instead of returning a string, so let's first rewrite this Caesar shift encryption method, but instead of returning a string, we're going to return a character because we're only interested in that particular character. So Caesar, so this Caesar encrypt, what do we call it? Caesar encrypt card. And then it's going to take in a car, C, and then again, we're going to have this key. And so instead of iterating over a string, we're just going to do it over one single character. And we're going to return that character. All right, so hopefully this makes sense. All I'm doing is I'm taking this function that we wrote, but instead of shifting it for every single character in the string, I'm just going to do it for a single character. And this will be, the return type of this will be a character. So now we have this is an encrypt card method. So let's write our Virginal encrypt method. Now encrypt, you go full screen, Virginal encrypt. It's going to take in, again, the original plain text. Now, with this, we have a key, okay? But so the key can be a variable length, but we want this key to sort of match the length of our original string. So instead of an integer this time, the key is a particular string, right? And we're going to just assume that, actually, we don't need to assume it. So what we're going to do is, first of all, let's build up this key such that it matches the length of the plain text. All right. So let's call this variable the final key. And we want it to match the length of the plain text. So let's again iterate over the plain text. And for each character, we don't care about the value of the character, but we want to add the matching key value. All right, so let's make this final key, add it to the final key, and the value we want to add is the value of, actually, instead of, because we need the position of the letter, we're going to do int I equals 0, I smaller than text.length plus plus. And so this is going to iterate over using this variable I. So we're going to start with I equals 0, I equals 1, I equals 2, all the way up equal to I equals plain text dot length minus 1, because with strings, just like in arrays, it's 0 index. So we start at 0 and not at 1. And so we want to stop right before we reach the length, the value of the length of the string. And so what we're going to do is increment this final key. Well, not increment, but add it to the final key. And we're going to just do plus equals key at I modulo key dot. I think this is the logic. What this is going to do, right? Say we have our key. So this is, say our ciphertext is hello curious, and our key is ABCD. Let's move it here so it's clear for you guys. Move this downwards. So our ciphertext is hello curious, and then this is our key. So we're going to go over the ciphertext, right? And this is going to just use I as a variable. We're going to originally our final key is empty, but for each value, so I starts at 0, we're going to take the value of the key at this particular position modulo the length of the key. So in this case, the length of the key is 4. So the first value is key at I modulo 4, which is 0 modulo 4, which is 0. So it's going to be A, then I is going to be 1, then 2, then 3. Once it reaches 4, right, this key only has a length of 4. So once it reaches 4, we want to take the modulo, because if you try key at 4, this is not going to work, because there's only the last value would be key at 3. So we want to take the modulo to make sure we don't go out of bounds. So Pranav, for the Caesar shift, yeah, if you wanted to decrypt, yeah, you could just take the negative value. And in this case, I just wanted to be a bit more clear. So, but definitely in the Caesar shift, if encrypting is the same thing as decrypting is the same thing as encrypting backwards. Like, so to decrypt it, you just need to encrypt it backwards. So the logic is the same. But I just wrote a separate function for it. But yeah, definitely it's the same logic, except you're going to the left instead of to the right. And you're doing, because yeah, and here it's the same thing. I could have used this function for encrypting. And here would just be a plus. Yeah. But I just made a separate function to make it clear. But anyway, so this would make the logic work, the final key. So now we have a key of the same length as ciphertext. So the key would be, let's make sure it's the same length, A, B, C, D, A, B, C, D, C, D, A, B, C, D, A, B, C. I think this is the same length. Final key. C, D, A, B, C, D, A, B, C, D. And while I'm doing this exercise, I'm assuming that everything's lowercase, because if I don't want to assume this, there might be some really dangerous mistakes, because capital A and lowercase a have different decimal values. And so if you have a key of like a shift of one has the value of 65 and one has the value of 97, they're both A's, but you shift by different amounts. It's going to make the logic a bit complicated. So for now, I'm just going to assume everything is in lowercase value. And then what we're going to do is we're going to iterate over each. So it's the same logic as the cipher encrypt. So let's take this logic here. This Rsa Encrypt. And let's paste. In this case, we don't need the modulo key. We have a ciphertext that we want to encode. So we're going to go over each of the plain text. And then, we want to do, let's do the int I again. Int I equals 0, I less than plain text dot length, I plus plus. We're going to use the ciphertext, and what we need to change is the key here, right? Okay, so actually C here would be the plain text at position I. And the key here represents the shift amount. So what is the shift amount? Okay, so remember the table. When we were at A, we would shift by 0. If we were at B, we would shift by 1, right? So what we can do is we can take this final key at that particular position. So the first value you take at this position 0, and then you subtract it by A. And this in parentheses, the final key at position I minus the character A, this represents the shift amount, right? So if this has a value of the character A minus I would be 0, so you don't shift it by anything. Whereas if it would be B minus A is 1, modulo 26 is 1. So then it would have a shift of 1. And then you take the modulo. The modulo is happening at the very end. Sorry. So let's make sure the parentheses are correct. Okay. Yeah, this is correct. And you do that for each of the ciphertexts. So this what I'm highlighting here is on a scale from 0 to 25, but we want to convert it back to a scale of I believe it was like 97, sorry, of 97 to 122. So then that's why you have to add A at the end. And this would encrypt the message. So let's just try it out. Let's comment out this, and let's, instead of using the Caesar encrypt, we're gonna do regional. And I'm realizing I'm going a bit, it's been an hour already, so I don't want to take too much time. I think we're making good progress here. So we're gonna encrypt regional, and the key would be, what do we want? Let's just make it as variable here. String key equals ABCD. Then this would be the key, right? And we comment this out and we run it. It's not going to work because it never works the first run, because I wrote these comments here. Just comment this out. All right, so let's see if this works. So we shifted A. This first one is shifted by A, so it's shifted by 0. So it should be A. This K is shifted by 1 because it's the letter B, so it's KL. So that's good. U is shifted by 2 because this is C, so then UVW, so shifted by 2. That is correct, and it seems like the whole thing is working, right? And this has, it should be the same length. Let's just double check this has the same length. Run this. This has a length of 6. This has a length of 6. So this will be the encrypted message. So to decrypt it, it's the same thing, right? But you need to shift it backwards. But you need the key. So encrypted message. Let's write our function. So regional decrypt, regional decrypt. Let's copy paste this. Very similar logic. You need the key. Final key is like this, but instead of shifting it to the right, we want to shift it to the left. So you do a minus, and then we want to add 26 just to prevent the negatives. And if we run this, we print it out. Let's see what the error is here. Rsa Decrypt. Okay, this I did not name this Rsa Decrypt. So now this is Rsa Decrypt. And you can't pass 2, you need to pass the key. And there we go. You encrypted this. So this is the message you send over. And hopefully your friend has the key that you gave them, which is ABCD. And so they take that key and then they process that encrypted message. And this is very hard to crack, right? Because you need to have if you don't have the key, then you don't really know how much to shift it by. Hopefully that made sense to you all. And that was the polyalphabetic cipher. So far we've looked at the monoalphabetic cipher and we've looked at the polyalphabetic cipher. Now you have to think back in the days, they were using their own hands and pen and paper to do this, right? Look how much simpler it is by programming. Like, sure, at first the logic might be a bit confusing, but once you have that, you can really automate it to any message you want. But back in the old days, they had to do this all by hand. Before I think transposition cipher is very interesting, but let's go first to polygraphic cipher. So remember at the beginning of this workshop, I was talking about two main branches of cipher. So we looked at substitution ciphering, so monoalphabetic, where we only use one alphabet, and then polyalphabetic, where we use these at least 2 or multiple alphabets to create this more complicated cipher that people had more trouble breaking into. There's even a better class of ciphers called the polygraphic ciphers within the substitution cipher. And the idea with the polygraphic cipher is that instead of just switching one letter around, you would switch group of letters around. Now, unfortunately, we don't have the time to code this tonight, but just want to introduce to you the Playfair Cipher. And the Playfair Cipher was a form of polygraphic substitution. Let's go to the Wikipedia page for the Playfair Cipher. And you guys can take a look at the logic. It's a bit more complicated, but you can definitely implement this with code. And essentially the idea is you, instead of encoding, as I said, one letter, you encode groups of letters. And the reason we do this is because with a single letter, it's easier to decode. So actually what I'm going to do is talk about frequency analysis right now. And so frequency analysis is this idea of cracking, is the way we really crack classical ciphers. Because with any method of ciphering, right? With any method of ciphering, what you're doing is still mapping a certain letter to another letter, regardless of like whichever way you do it, you're still doing that. But the problem is that, you look at certain letters in the English language. If I'm saying something to you, there's certain letters in the words that appear more often. So if you look at the graph here, you realize that the letter E occurs the most often in the alphabet, right? And if we look at my cipher, if it was a long enough message, right, you study the occurrence of each word and you try to count how many times the occurrence of each character, and you try to count how many times that character appears. The one that appears the most often, that character is very likely to be the letter E. Now, that's why the Playfair Cipher, I guess, kind of tries to get over that problem. It makes it a bit harder when you group groups of characters. It becomes a bit less susceptible to the frequency analysis, because if you do like a Caesar cipher, or even if you do a Caesar cipher, then you sort of have these occurrences happen. You can see it will be different characters, but you're going to see the sort of the same pattern. The polyalphabetic cipher, it resisted all attempts to break until 1863. It becomes a bit harder, right? Because you're shifting each letter by a different amount. So the letter E and your final encrypted message, it's not going to be obvious. Even if it's the one that appears the most, that's probably not the letter, might not be the letter E. I need to drink some water, so give me 10 seconds. Yeah. And so polygraphic cipher makes it again a little bit harder for the frequency analysis to be happening and cracking that. There's another family of ciphers called the transposition cipher. And this is, instead of just switching characters around, what you're going to do is do a sort of permutation. So you're going to move the letters around. Each of these letters still have the same meaning. So you're not going to say like, oh, I now is represented by B, C is now represented by D. You're not going to do that. You're going to just switch the order of the letters around. And hopefully that will confuse your enemy or whatever enough. And so what they did back in the 7th century BC was using the Cytel. And so what would happen is, you see this is like a strip of parchment. Of parchment, I think that's what it's called. A strip of parchment, sorry. And let's give me a presenter view. It's a strip of parchment. And then you wrap this around this thing called a Cytel, right? And so after you wrap it around, you can write your message like this. And the thing is, after you unwrap this, you're gonna just see, you won't see this original message like this, but you're gonna see instead, you're gonna read this like vertically. So in this case, if the original message was like, I am heard very badly, help, you're gonna write it like this in rows. But after you unwrap it, you're only gonna read it like IRYY ATBH MVAE, etc. And so that makes it very confusing for the opponent, because if you try a frequency analysis or whatever, just like looking at the occurrence of the letters, it's going to be a bit harder because that's not going to help you. You're going to need to be able to find out exactly how the way the words are not grouped together next to each other. So they're actually moved around. And so what you need to do, when you intercept this, if you know it's a transposition cipher, there's also another layer of complexity because you need the exact same Cytel with the same diameter. Because if you don't have the same diameter, even if you wrap it around, you can't. It's not aligned perfectly. And so this was an idea employed back in the 7th century BC. As an exercise, I want you guys to try implementing this one, the transposition cipher. Again, it's gonna, if you guys need help, definitely reach out to me, but you're gonna need to use modular arithmetic for this one as well. And so the idea is that you're gonna, for example, this one is every 5th you change rows. You use modular arithmetic to encode and decode this one. That's all the hints I'm gonna give you. I was planning on maybe doing this one with you guys, but because we're a little out of time, I'm gonna skip this part. And as well, if you want to challenge, do the Playfair Cipher. Try to implement this one in code. I think they're really good exercises if you want to really hone your programming skills. For frequency analysis, I wanted to do an exercise with you guys just to showcase how you would go about cracking some sort of cipher. I'm not going to do it in code because you could, but because we again don't have enough time, I'm going to show you guys an example. So here we have an original ciphertext. Okay, let's do this exercise together. So I want you guys to tell me, how do we first go about, from what I just told you guys, how do we go about cracking the ciphertext? Assuming, for example, you know that this is some sort of substitution cipher method. What's the first step we would try to decode the ciphertext? Anyone? Okay, say if you tried to brute force the Caesar shift, it doesn't work. You tried all possible combinations, it doesn't work. So you know it's something more complicated than the Caesar shift. And let's say it's not the It's not the Vision cipher. Okay, it's a bit more simpler. So when I was talking about the mapping, like say, you were mapping. Don't say this one. Let's do a paint. Assume it's some sort of mono-alphabetic cipher. So I change the letter A to letter D. I change the letter B to letter C. I change the letter C to letter Z, letter D to letter F, etc. So this sort of ciphering method. How would you go about solving this with frequency analysis? And then that would be monoalphabetic. Okay, you just saw the answer right there. But essentially, the first thing you would do, right? You look at the occurrences of each letter. And so that's what we do here. We you can write a program that goes over this. And remember, I was talking about dictionaries and maps, right? You go over the string, and then for each one, you use the map, store the occurrences of each character. And from that, we see that I is the most common single letter. But we can also look at groups of letters. So when you talk about bigram, that's groups of 2 letters, and trigram is groups of 3 letters. We notice that I is the most common single letter, XL is the most common bigram, and XLI is the most common trigram. Now, in the English alphabet, E is the most common letter. And see if XLI, if it corresponds to THE. And so that's what we do. We replace the X with the T, L with the H, and I with the E. So lowercase represents what we've changed, and I represents the original message, the original ciphertext. So all we did is change the X with the T, L with the H, I with the E. And from here, now we try to continue finding patterns of words. So for example, we can see that here we see at, that, and then TMZE. We can maybe guess that TMZE would be time, right? At that time, at that TMZE would be at that time. So we try to guess that, and then from that we can sort of guess that the M capital would be I. And we also see that there's R Tate, that is most likely state. So you guess the R is yes, all right? And so you sort of do this trial and error and see if it works. And then once you have like most of the common words guessed, like you can very easily, I guess, guess the Z's, guess the W's, guess the X's. And finally, you have this message. And all we need to do at the end is add the punctuation. And there you have it. This is a decrypted ciphertext. Awesome. So now we're going to go and watch a video together. So this is a crash course video. I hope you guys can watch it. I think they give a very good introduction. Some of the things I talked about in this workshop where already they talk about it at the beginning of the video. But in the second part, they talk more about modern cryptography. So I wanted to showcase this video as a way to introduce it to you guys. And we're going to have a great discussion. And I'm going to show you guys some more really cool modern tools on how we encrypt and decrypt things. So let's go and watch this video. I need to stop sharing. And I will share my audio. So speakers, share cryptography, and then share. Can you guys let me know if you hear the audio? A thumbs up or a yes. You can't hear it? Okay. Okay, thanks for letting me know. I'm gonna try stop sharing. Screen. Share sound. Okay, I forgot to share sound. That's why.
Security.
Okay.
Hi, I'm Carrie-Anne and welcome to Crash Course Computer Science. Over the past 2 episodes, we've talked a lot about computer security, but the fact is there's no such thing as a perfectly 100% secure computer system. There will always be bugs, and security experts know that. So system architects employ a strategy called defense in depth, which uses many layers of varying security mechanisms to frustrate attackers. It's a bit like how castles are designed. First, you've got to dodge the archers, then cross the moat, scale the walls, avoid the hot oil, get over the ramparts, and defeat the guards before you get to the throne room. But in this case, we're talking about one of the most common forms of computer security, cryptography. The word cryptography comes from the roots crypto and graphy, roughly translating to secret writing. In order to make information secret, you use a cipher, an algorithm that converts plain text into ciphertext, which is gibberish unless you have a key that lets you undo the cipher. The process of making text secret is called encryption, and the reverse process is called decryption. Ciphers have been used long before computers showed up. Julius Caesar used what's now called a Caesar cipher to encrypt private correspondence. He would shift the letters in a message forward by 3 places, so A became D and the word Brutus became this. To decipher the message, recipients had to know both the algorithm and the number to shift by, which acted as the key. The Caesar cipher is one example of a larger class of techniques called substitution ciphers. These replace every letter in a message with something else according to a translation. A big drawback of basic substitution ciphers is that letter frequencies are preserved. For example, E is the most common letter in English, so if your cipher translates E to an X, then X will show up the most frequently in the ciphertext. A skilled cryptanalyst can work backwards from these kinds of statistics to figure out the message. It was the breaking of a substitution cipher that led to the execution of Mary Queen of Scots in 1587 for plotting to kill Queen Elizabeth. Another fundamental class of techniques are permutation ciphers. Let's look at a simple example called a columnar transposition cipher. Here we take a message and fill the letters into a grid. In this case, we've chosen 5 by 5. To encrypt our message, we read out the characters in a different order. Let's say from the bottom left working upwards, 1 column at a time. The new letter ordering, what's called a permutation, is the encrypted message. The ordering direction, as well as the 5 by 5 grid size, serves as the key. Like before, if the cipher and key are known, a recipient can reverse the process to reveal the original message. By the 1900s, cryptography was mechanized in the form of encryption machines. The most famous was the German Enigma, used by the Nazis to encrypt their wartime communications. As we discussed back in episode 15, the Enigma was a typewriter-like machine with a keyboard and lampboard, both showing the full alphabet. Above that, there was a series of configurable rotors that were the key to the Enigma's encryption capability. First, let's look at just one rotor. One side had electrical contacts for all 26 letters. These connected to the other side of the rotor using cross-crossing wires that swapped one letter for another. If H went in, K might come out the other side. If K went in, F might come out, and so on. The letter swapping behaviour should sound familiar. It's a substitution cipher, but the Enigma was more sophisticated because it used 3 or more rotors in a row, each feeding into the next. Rotors could also be rotated to one of 26 possible starting positions, and they could be inserted in different orders, providing a lot of different substitution mappings. Following the rotors was a special circuit called a reflector. Instead of passing the signal onto another rotor, it connected every pin to another and sent the electrical signal back through the rotors. Finally, there was a plug board at the front of the machine that allowed letters coming from the keyboard to be optionally swapped, adding another level of complexity. With our simplified circuit, let's encrypt a letter on this example Enigma configuration. If we press the H key, electricity flows through the plug board, then the rotors, hits the reflector, comes back through the rotors and plug board, and illuminates the letter L on the lamp board. So H is encrypted to L. Note that the circuit can flow both ways. So if we type the letter L, H would light up. In other words, it's the same process for encrypting and decrypting. You just have to make sure the sending and receiving machines have the same initial configuration. If you look carefully at this circuit, you'll notice it's impossible for a letter to be encrypted as itself, which turned out to be a fatal cryptographic weakness. Finally, to prevent the Enigma from being a simple substitution cipher, every single time a letter was entered, the rotors advanced by 1 spot, sort of like an odometer in a car. So if you entered the text AAA, it might come out as BDK, where the substitution mapping changed with every key press. The Enigma was a tough cookie to crack for sure, but as we discussed in episode 15, Alan Turing and his colleagues at Bletchley Park were able to break Enigma codes and largely automate the process. But with the advent of computers, cryptography moved from hardware into software. One of the earliest software ciphers to become widespread was the Data Encryption Standard, developed by IBM and the NSA in 1977. DES, as it was known, originally used binary keys that were 56 bits long, which means that there are 2 to the 56, or about 72 quadrillion different keys. Back in 1977, that meant that nobody, except perhaps the NSA, had enough computing power to brute force all possible keys. But design $250,000 every possible DES key in just 2 days, rendering the cipher insecure. So in 2001, the Advanced Encryption Standard AES was finalized and published. AES is designed to use much bigger keys, 128, 192 or 256 bits in size, making brute force attacks much, much harder. For a 128-bit key, you'd need trillions of years to try every combination, even if you used every single computer on the planet today, so you'd better get started. AES chops data up into 16-byte blocks and then applies a series of substitutions and permutations based on the key value, plus some other operations to obscure the message. And this process is repeated 10 or more times for each block. You might be wondering why only 10 rounds, or why only 128-bit keys and not 10,000-bit keys? Well, it's a performance trade-off. If it took hours to encrypt and send an email, or minutes to connect to a secure website, people wouldn't use it. AES balances performance and security to provide practical cryptography. Today, AES is used everywhere, from encrypting files on iPhones and transmitting data over Wi-Fi with WPA2 to accessing websites using HTTPS. So far, the cryptographic techniques we've discussed rely on keys that are known by both sender and recipient. The sender encrypts a message using a key, and the recipient decrypts it using the same key. In the old days, keys would be shared by voice or physically. For example, the Germans distributed codebooks with daily settings for their Enigma machines. But this strategy could never work in the internet era. Imagine having to crack open a codebook to connect to YouTube. What's needed is a way for a server to send a secret key over the public internet to a user wishing to connect securely. It seems like that wouldn't be secure, because if the key is sent in the open and intercepted by a hacker, couldn't they use that to decrypt all communication between the two? The solution is key exchange, an algorithm that lets two computers agree on a key without ever sending one. We can do this with one-way functions, mathematical operations that are very easy to do in one direction, but hard to reverse. To show you how one-way functions work, let's use paint colors as an analogy. It's easy to mix paint colors together, but it's not so easy to figure out the constituent colors that we use to make a mixed paint color. You'd have to test a lot of possibilities to figure it out. In this metaphor, our secret key is a unique shade of paint. First, there's a public paint color that everyone can see. Then John and I each pick a secret paint color. To exchange keys, I mix my secret paint color with the public paint color. Then I send that mixed color to John by any means, mail, carrier pigeon, whatever. John does the same, mixing his secret paint color with the public color, then sending that to me. When I receive John's color, I simply add my private color to create a blend of all three paints. John does the same with my mixed color, and voila! We both end up with the same paint color. We can use this as a shared secret, even though we never sent each other our individual secret colors. A snooping outside observer would know partial information, but they'd find it very difficult to figure out our shared secret color. Of course, sending and mixing paint colors isn't going to work well for transmitting computer data, but luckily mathematical one-way functions are perfect, and this is what Diffie-Hellman key exchange uses. In Diffie-Hellman, the one-way function is modular exponentiation. This means taking one number, the base, to the power of another number, the exponent, and taking the remainder when divided by a third number, the modulus. So for example, if we wanted to calculate 3 to the 5th power modulo 31, we would calculate 3 to the 5th, which is 243, and then take the remainder when divided by 31, which is 26. The hard part is figuring out the exponent given only the result and the base. If I tell you I raised 3 to some secret number modulo 31 and got 7 as the remainder, you'd have to test a lot of exponents to know which one I picked. If we make these numbers big, say hundreds of digits long, then finding the secret exponent is nearly impossible. Now let's talk about how Diffie-Hellman uses modular exponentiation to calculate a shared key. First, there's a set of public values, the base and the modulus, that, like our public paint color, everyone gets to know, even the bad guys. To send a message securely to John, I would pick a secret exponent, x. Then I'd calculate b to the power of x modulo m. I send this big number over to John. John does the same, picking a secret exponent y and sending me b to the y modulo m. To create a shared secret key, I take what John sent me and take it to the power of x, my secret exponent. This is mathematically equivalent to b to the xy modulus m. John does the same, taking what I sent to him to the power of y, and we both end up with the exact same number. It's a secret shared key, even though we never sent each other our secret number. We can use this big number as a shared key for encrypted communication, using something like AES for encryption. Diffie-Hellman key exchange is one method for establishing a shared key. These keys that can be used by both sender and receiver to encrypt and decrypt messages are called symmetric keys because the key is the same on both sides. The Caesar cipher, Enigma, and AES are all symmetric encryption. There's also asymmetric encryption, where there are two different keys, most often one that's public and another that's private. So people can encrypt a message using a public key that only the recipient with their private key can decrypt. In other words, knowing the public key only lets you encrypt but not decrypt. It's asymmetric. So think about boxes with padlocks that you can open with a key. To receive a secure message, I can give a sender a box and a padlock. They put their message in it and lock it shut. Now they can send that box back to me and only I can open it with my private key. After locking the box, neither the sender nor anyone else who finds the box can open it without brute force. In the same way, a digital public key can encrypt something that can only be decrypted with a private key. The reverse is possible too, encrypting something with a private key that can be decrypted with a public key. This is used for signing, where a server encrypts data using their private key. Anyone can decrypt it using the server's public key. This acts like an unforgeable signature, as only the owner, using their private key, can encrypt it. It proves that you're getting data from the right server or person and not an imposter. The most popular asymmetric encryption technique used today is RSA, named after its inventors Rivest, Shamir, and Edelman. So now you know all the key parts of modern cryptography: symmetric encryption, key exchange, and public key cryptography. When you connect to a secure website like your bank, that little padlock icon means that your computer has used public key cryptography to verify the server, key exchange to establish a secret temporary key, and symmetric encryption to protect all the back and forth communication from prying eyes. Whether you're buying something online, sending emails to BFFs, or just browsing cat videos, cryptography keeps all that safe, private, and secure. Thanks, cryptography! Crash Course Computer Science is produced in association with...
All right, I hope you guys enjoyed that. It was 12 minutes. So is there any questions about anything you guys saw in the video? I think there were a lot of terminology thrown around: modular exponentiation, symmetric key encryption, asymmetric encryption, Diffie-Hellman exchange. So I think it's a lot to take in, but hopefully you guys learn a little bit. The first part, she talked about Caesar shifts, Caesar ciphers, transposition ciphers, and the substitution ciphers, frequency analysis. So it's a lot of things we talked about in today's workshop was covered in that video. But I think for this final part of the workshop, what I want to do with you guys is showcase some of the ways we can encrypt with these modern techniques. So one of the things she mentioned in the video is, let me stop sharing, and I'm going to share my screen instead of, I'm going to share my screen. Okay, and hopefully you guys see this. And we're going to go onto a really cool site called CyberChef. And within this site, they have like all these algorithms that are already there. So we're going to play around with some of them. Actually, we're going to play with one called the Rsa Encryption. So remember, she talked in the video about this idea of the Rsa, which is the most popular asymmetric encryption method. So the thing with asymmetric is that you have both a public key and a private key, right? And so the idea is, for example, I want you to send me a message, okay? So what I'm going to do is I'm going to give you a lock and a container, a lock with the key, what is it? A box and a lock to lock the box, okay? And I hand that over to you, and then you're going to put your message inside this box, and you're going to lock it with the public key. And because I have the private key, you can send that over, like someone else can intercept this box, but because they don't have the private key, they can't unlock that box. And only I, the person with the private key, can unlock this box. I am able to read that message. So let's see how that works in practice. So RSA, what we're going to do is first generate a key. So I actually want you guys to try this with me. So the link is CyberChef. And what I want you guys to do is generate a key first. So RSA, and let's generate an Rsa Key Pair. And so we have multiple options here. Let's just take the simplest one. I think by the usually it's at least 2048 or 49.6, but let's just take 1024. Basically, the longer the key, the safer it is because there's more possibilities and it's harder to crack. And when we generate a key, we're going to have two things. One, the public key, and two, the private key. Now, usually you never, ever, ever share your private key, okay? Like never screen share with someone showing your private key because that is very, very dangerous. But here we're just taking some random public and private key that I'm not going to use, but we're going to use it for demonstration purposes. So what I would do is I would give this public key to you guys. So I just sent it in the chat, right? This is the public key. So all of you guys now have the access to the public key, and I have access to my private key. So I'm going to store this on Notepad. I'm going to paste this. So I have my public and my private key. Okay. So then what we can do is we can do Rsa encryption. Right. So let's do Rsa encryption. So we're going to take this public key that I have, and you guys can do the same exact thing. You're going to take this and you're going to write a message that you want to write to me. So say, hi, Steven, this is Zach, for example. All right. So what RSA does, it takes this message, it's going to use this public key, and it's going to lock this message into this particular format, this particular message, right? And if you want to decrypt it, you're going to apply the Rsa Decrypt algorithm. And then now I'm going to use my private key, because only I can decrypt this message if I have the private key. And there you go. You can see that this is decrypted. Now, just to prove that this only works with my key, if I go on CyberChef again and I try to generate another key. So in public key, let's go here. Public key. Oh my God, public. And let's do generate another one. Let's do Rsa generate key pair. If I use this other, say, public key, I'm gonna try this. It says that it is invalid, right? So, and that is why it only works with my particular key. So if I try this key instead, it works, okay? So now what I want you guys to do is maybe, let's try it. If you want to send me a message, you guys want to send me a message, and I'm going to try and decrypt it. And so you guys can just copy the output of Rsa Encrypt. And usually actually when we do encryption, we convert the message in base 64. So because this is sort of very hard to handle text, what we can do here in data format, you can convert it to base 64, and that's going to make some super clean text. And so you guys can paste that in the chat, for example, and then I'm going to convert this back from base 64 into this original format, and then I can decrypt it using my public key, using my private key. Sorry, Rsa Decrypt. Then I can paste my private key. And there you go, we have this message. So whatever I do, it's just gonna work. Another thing that was talked about in this video was the idea of signatures. Now, for signatures, the reason we use this is, remember at the beginning of tonight, I was talking about how cryptography serves two main purposes. Number one is keeping secrets, and number two is proving identity and knowledge. And so for this point, proving identity and knowledge, how do I prove that I was the one who sent you this message? Well, what I can do is do something called signing. And in this case, what we're going to actually sign with our private key. So we're going to take a private key, and we're going to sign this. All right, and this is going to generate some output, and I'm going to give that to the other person, and I'm going to claim that I'm going to send them. Everyone has access to my public key, right? And so if I am actually the person who owns both the public and private key, if I send them this and they try to verify it with the public key, it should work. But if it's any other person who tries to impersonate me and saying it's me, and I send out some random string, it's not going to work. when they apply the public key. So for example, if I do here, I first signed it, and then if someone wants to verify it with my public key, verify that those two are together. Oh. So I think I tried this. Yeah, sometimes I was running into issues on why it wasn't working. This is my public key. Okay, let's generate a new one. Right here. I'm going to sign this. So Rsa private key. I'm going to copy my private key. It's going to generate this message. And let's and then Rsa verify. Our public key. I think the reason was Rsa verify. Oh, I think I cannot. Yeah, I was trying this. I cannot have anything in the input for some reason. So yeah, this works, but it's just I can't put anything in the text field here. So this is I've signed it, and then let's verify it. And then it says verified. Okay, yeah. So if I put some text, for some reason it fails the verification, because I guess you don't really attach text when you just do the signatures. And those were sort of the introduction to the Rsa algorithm. I actually learned the Rsa, like how the math in it, back in September 2021 for school. And I can quickly show you guys. This is the encryption algorithm that you do. Yeah, we did math for this. But basically, you got to choose two large distinct prime numbers. You take GCDs, do modular arithmetic, solve. Here you see a modular exponentiation, and then for decryption, this is what you do. I'm not going to go into the details, and to be honest, I'm also a little bit rusty on this, but it's very interesting how far we've come and how we've used math nowadays to make sure that our message doesn't get decrypted or cracked by hackers, because our computers are just getting way too powerful. And one last thing I want to talk about for tonight is the arrival of potentially quantum computers, which might really compromise the security of everything, because as you guys probably know, like quantum computers are so much more powerful than our regular computers, which work in binary. The thing with quantum computers right now, these algorithms that we have, so for example, when we're generating this Rsa private key, we could specify the key length, right? And so the longer the key length, the harder it is to crack it. And the way we crack things is by basically brute forcing it, right? You try different possibilities. But a regular computer, I guess, if you try to brute force this one, it's going to be too slow. But with the rise of quantum computers, it might be able to brute force things in a way faster way than our regular computers. And so these might no longer be safe. Just like if you remember the video, they were talking about the data encryption standard, but because computers got so powerful, like a regular computer could crack it in 2 days. And so we might see something very similar happening with these encryption algorithms that we have today. And so we need to adapt in the future. But so far, we don't have any quantum computers that are able to achieve and undermine all of our security things. And they're not able to brute force. And so that's why for now, we are in good hands. But there's a whole field of quantum computing for cryptography, quantum cryptography. You guys look at the Wikipedia, and they're looking at studying how we can use quantum to perform these cryptographic tasks, and sort of researching how quantum computers can break cryptography. So this is a field of study that is right now happening to make sure that in the event that it breaks, like how bad would it be? And I think that is sort of the end of the workshop. I really hope you guys enjoyed. There was quite a lot of information. Haven't given a workshop in a bit of time, but it was really I really enjoyed this. So I hope you guys enjoyed. If you did, make sure to stay around. There's tons of workshops for the Learnathon, and this was the first one on cyber. Yeah, if there's anything I can improve or there's any feedback for the team, please send us a message. We usually do surveys at the end of the event, but if you guys have feedback for us right now, it would also be really appreciated. Feedback from me personally as well would be really appreciated. So yeah, that's pretty much it. Thank you guys, and I'll see you guys soon. And make sure to go to our other events, our other workshops, because we have tons of great speakers lined up. So thank you all.